Welcome back. This is part two of our practice test video. Since I'm in my office, I have my video on so I can tell you things. So continuing, question 11. If we have to list the elements of the following set, right, make sure you follow instructions, right? You have to list the elements. And we have the first set is Al, Bob, Chris, and Dave. And then we have to remember what this means. Right? This is, I like to put a little bar between to remind myself that it's and. Right? Which means only the overlap, right? And so if an element is in both sets, then it's in this and set. So is there an Al in the second set? No, there isn't. Okay. Is there a Bob? Yes, there is. Is there a Chris? Yes, there is. Is there a Dave? Yes, there is. And moving on to the only one that we didn't cover in the second set, which is Ed. And so combined, I have the set. So list the elements. I have Bob, Chris. Oops, that's a weird way of writing Chris. Chris and Dave. Nice. Easy. The alternative would be or, right, which is the U, right? And then if it was or, then it would be all the elements in the first set as well as all the elements in the second set, right? Uh, Not writing out any overlap. We don't write overlap, or I should say duplicate elements. Huh? Question 12. If we have a universal set 1 through 10, and A is 1 through 5, B is 1, 3, 4, 6, and C is 2, 4, 6, and we want to list the members of this kind of compound set here. So what we need to do is we need to break this down. Okay? And just like in logic, you're going to start with the negation first, right? And so you have A or B, but then you want the composite or complement, words. You want the complement of it. Okay? Then and C. Okay. And so what we're going to do is first we need to find A or B. Now A or B, it's good practice, right, is all the elements in A or B, or both. Okay. So I'm going to start with the elements of A because that's 1, 2, 3, 4, 5. So I know those have to be in here. 1, 2, 3, 4, 5. And then I'm going to tack on the elements of B that I have not listed yet. Okay. I have 1, I have 3, I have 4, I don't have 6. And so I'm going to add that on and close my set. Okay. Then I need to find the complement of A or B. The complement, remember, is every element in the universal set that is not in A or B, which means all the elements that are not 1, 2, 3, 4, 5, 6, right, in the universal set, which means that I have 7, 8, 9, and 10 in the complement of A or B. Now to build out final stage here, so I have the complement of A or B and C. So it can be in 7, 8, 9, 10, as well as in C, 2, 4, 6. Okay. Now, I don't see any overlap here. I don't see a 2, I don't see a 4, I don't see a 6, which means there are no elements in this set, and I get the empty set. Okay. Or if you prefer to write like this, just empty brackets with nothing in it. Okay. You may not write like this. Okay. You may not write this because this has an element of 0, but 0 isn't even a player, and so it wouldn't make sense to write that. So you can do empty curly brackets or use the empty set notation, right? But you cannot do this, right? Because it's not the empty set. Because it's not the empty set. Huh? Just as a heads up. I see that commonly, and so that's why I want to point that out. Okay, nice. In Mrs. Yamamoto's class of 35 students, 12 students are taking history, 18 are taking English, and 4 are taking both. We want to draw a Venn diagram and find the number of students in each region of the Venn diagram. So I have history, so students taking history, I have students taking English, and I have some taking both, which tells me that I have 2 sets with some overlap. And so in terms of A here, I have a 2-circle Venn diagram. And I have some taking history and some taking English, and of course, some taking both. Out here, you have everyone who is taking neither. And so here's the universal set denoted by the rectangle. Okay. How you want to tackle the Venn diagrams, remember, is to start at the very innermost area, right? And then subtract that area as you move out. So 4 are taking both. So we start here, 4 are taking both, which means that a total of 12 have to be taking history, right? Which means that 12 minus 4, because I've already listed 4 of them taking both, means that 8 are taking only history. Okay. And 18 are taking English. Now, 18 is the total E circle, which means that 14 are taking only English. Okay. And finally, the last region, we have 35 students, but I've already listed 8 plus 4 plus 14 of those, and so I'm going to take that away, right? And so I get 35 minus 8 minus 4 minus 14 puts me at 9 out here. Okay, and I'll show where I got that from. Right, 35 minus 8 minus 4 minus 14. Okay. So that's part A. Draw a Venn diagram and find the number of students in each region of the diagram. Now I have shown how many are in each region, so I'm good. How about B? How many students are taking neither history nor English? Okay? So they're not in the H circle and they're not in the E circle, which means they're out here. And since you've shown your work up above, then you can just say 9, right? Nice. I'm going to keep this one on its own page because it'll be quite large, I think. Or can I squeeze it in? Nah, it's virtual paper, so let loose. A survey of 100 students at a college finds that 50 take math, 40 take English, and 30 take history. Now I'm talking about 3 things, which means I know I'm going to have a 3-circle Venn diagram. Okay? And then I'm given some more information. Of these, 15 take English and math, 10 take English and history, and 10 take math and history, and 5 take all 3 subjects. Okay? And of course, A, draw a Venn diagram and find the numbers in each region of the diagram. So that's probably the most work for this question. So let's get started. So we already established this is a three-circle Venn diagram. And make sure you have some overlap here. And of course, it's possible that there are people taking none of them. Let's label these. I like to label them like this: math, English, and history, kind of moving around clockwise, I guess, in the order that the subjects appear. And then my next one, then this is the universal set. My next step is to start in the very, very center and then bloom my way out, right? So I'm going to start here with 5, take all 3 subjects. So I know I have 5 in this region. Working backwards, 10 take math and history. So math and history. Total of 10 in the overlapping region. Now I've already written down 5, which means I have 5 left. 10 take English and history. English and history is here, and so this total region must be 10, but I already have 5 written out, so I have 5 again. 15 take English and math. English and math. I've already got 5 of those accounted for, which means that I have 10 here. Now, 30 take history. Okay, which means that my total H circle has to add to 30. But I already have 5 plus 5 plus 5 accounted for, which means I have 15 taking only history of these 3 subjects. 40 take English, which means the full E circle has to be 40, but I already have 20 of these guys. And same thing for math, 50 take math, but I already have 20 of these guys. And so I have 30 taking math. Now to figure out the outside region, right, it's a little bit tedious, but we have 100 students, right? And so the total rectangle has to be 100, but I've already accounted for all these. And so I'm just going to jot it down here. Oops. This number is going to come from 100 minus 30 minus 10 minus 20 minus 5 minus 5 minus 5 minus 15. Just move methodically. 30 minus 10 minus 20 minus 5 minus 5 minus 5 minus 15. So I get 10 out here. Nice. There. Now that's part A done. Now I think B, C, and D are relatively quick in comparison, so let's see what we can do here. B, find the number of students taking math, but not the other 2 subjects, right? And so they have to be taking math, but not the other 2, which is 30. Now, because you have these numbers here, you're allowed to just put the number as your answer. And so here, 30. When I'm marking, I will make sure that whatever answer you give me here matches what you wrote here. So even if your Venn diagram is wrong, which is going to be most of your marks, right? As long as you use your Venn diagram to give me the appropriate answer, I'm happy. C, how many students are taking English or math, but not history? And so they can be in English or math, but they can't be in this history bubble. Okay? And so they can be in 30 plus 10 plus 20. 30 plus 10 plus 20. which is 60. And how many students are taking none of these subjects? Well, that's going to be the 10 from above. Nice. For lunch, a small restaurant offers 2 types of soups, 3 kinds of sandwiches, and 2 types of soft drinks. Now, I'm going to fix this because it says use a tree diagram, but it'll just say determine the number of possible meals consisting of a soup, sandwich, and a soft drink. Okay, and so here I will make a note that you could solve with slots or a tree diagram. But as promised in class, you don't have to show a tree diagram. If you prefer the slots, that's okay. What would the slots look like? The slots would look like this. You have a soup, you have a sandwich, and you have a soft drink. You have a soup and a sandwich and a drink, meaning you multiply. Whenever you use the slots, though, you will be multiplying. You have 2 types of soup, 3 kinds of sandwiches, and 2 types of soft drinks. So 2 times 3 times 2 puts me at 12. Huh? Just want to show you what the tree would look like. Totally optional. As long as you do one of these, right? The question is only asking for for you to determine the number of possible meals, right? The number of possible meals is 12. So 12 possible meals, I guess, if we're being proper. But I want you to see the tree. So first you have your soup 1, soup 1, soup 2. And then from there, you have your sandwich. Let's call it W for sandwich, because I don't want to use the same letter. W1, W2, W3. And then drink 1, drink 2, drink 1, drink 2, drink 1, drink 2. You can see why I prefer the slots, but this will work if you want to visualize it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 branches. When would the tree be useful? You would need the tree to list all the possible meals, right? We would use a tree if we needed to list all the possible meals. Huh? Nice. Question 16. How many 7-digit telephone numbers are possible if the first 2 digits cannot be ones or zeros? Okay. So if we have 7 digits here, I'm going to solve this with slots. I think it's the easiest thing to do here. 1, 2, 3, 4, 5, 6, 7 digits. The first digits not one or zeros. Huh? Now remember how many digits there are. 0 through 9, there are 10 digits, right? When we remove two of those options, right, and you can count it out, right? 2, 3, 4, 5, 6, 7, 8, 9. Huh? That leaves me with eight possibilities. Huh? And so here I have 8, and here I have 8. There's no mention of, oh, you can't have repeating numbers or anything like that. That's okay. We just have the restriction that we can't have ones or zeros in the first two numbers. But then I'm open to all 10 digits. So how you solve these, you'll always want to tackle your restrictions first and then fill in the blanks or fill in the rest, I guess. This is going to be quite large, so I'm going to move this over here. 8 times 8 times 10 to the power of 1, 2, 3, 4, 5. I get 6, 4. 1, 2, 3, 4, 5. 1, 2, 5. 6.4 million phone numbers, 7-digit phone numbers can be made with those restrictions. A coin, question 17. A coin is tossed 3 times and the sequence of heads and tails is recorded. Use a tree diagram to determine the different possibilities. Okay. Now, because I want those different possibilities, that is when I would use a tree diagram. Because if I want to list all the possibilities, I need a tree to do that, because otherwise it can be really hard to wrap your head around. So I toss a coin 3 times, and I have heads or tails, so this is toss number 1. And it doesn't matter what happened on the first toss. For toss number 2, I could have heads or tails. And for toss number 3, again, I could have heads or tails. Nice. Now all I need to do, because the question says to determine the different possibilities, so now I have to list them all, and the natural place to list them here would be at the end of each of these branches, reading down HHH, HHT, HTH, HTT, THH, THT, TTH, and TTT. And that's fine. You don't have to list them in any fancier way, right? This is the answer. Huh? Okay. The sets and counting section is always way faster than the financial math. Question 18. A group of 15 people who are members of an investment club wish to choose a president and a secretary. How many different ways can this be done? Now, if I have someone who's chosen to be the president, they can't be the secretary, right? And same thing, if I choose for someone to be the secretary, they can't be president as well. And so I like to solve this with slots. But since the order matters, right? Let's assume that I pick a president first and then I pick a secretary, right? Then it's a permutation. Okay. So I have my president, and then I choose my secretary. Now we have 15 people, and they're going to pick one of them to be the president. So 15. But then when I've used a person as the president, I only have 14 people left. And so now I have 15 times 14, which means I have 210 ways to do that. Or if you prefer, you could use 15p2, which is 210. That's fine as well. Okay, nice. How many permutations of the letters of the word security end in a consonant? Now, here we have this pickle again, especially because we have a Y in here. Let's say Y is a vowel, right? A, E, I, O, U, and sometimes Y. Let's assume Y is a vowel, which makes it not a consonant. All right. Now, what I want to do is I want to have the same number of letters, and I want to know how many ways can I scramble them where I force them to end in a consonant, which means that first I need to count how many letters I have. 1, 2, 3, 4, 5, 6, 7, 8 letters. 2, 3, 4, 5, 6, 7, 8. And I want to force this last one to end in a consonant. Now, how many consonants do I have if Y is considered a vowel? I have 1, 2, 3, 4. 4 consonants. And then E, U, I, Y, 4 vowels. Depends on if you consider a Y consonant or a vowel. But in this case, it's a vowel. So as before, you want to tackle your restrictions first, right? Which means you're going to force this to be a consonant. Now you have 4 consonants to choose from, which means you've already kind of used one of your letters, one of your 8 letters, which means when you start over here, you only have 7 letters left, right? And so you have 7, and then 6, and then 5, and then 4, and then 3, and then 2, and then 1. Multiplying this out. If you're kind of more familiar with factorials now, right, this would be 7 factorial times 4. Okay, but I'm just going to do it 7 times 6 times 5 times 4 times 3 times 2 times 1 times 4. And I get 20,160 different permutations. Okay. Question 20. A bakery has 9 different fancy cakes. In how many ways can 5 of the 9 fancy cakes be lined up in a row in the bakery display case? So this is one of those scenarios where you need to start asking yourself, okay, does the order matter, right? And so if you think about your display case, cake 1, 2, 3, 4, 5, right? Cake number 1, number 2, number 3, number 4, number 5. Now that would be different if I had different cake numbers here, right? And so order matters in this cake. Case. Pun intended, I guess. Or error intended. So, how many cakes do I have to choose from for my first spot? Well, I have all 9. Now, I've used one of the cakes in my first spot, which means I only have 8 left, and then 7, and then 6, and then 5. Which 9 times 8 times 7 times 6 times 5, which is 151, or sorry, 15,120 different ways. Or, let's see here. Or, once you've decided that order matters, right, and there are no restrictions that you're dealing with. So up here, we couldn't really use permutations because we had restrictions that we had to take into account. And so then the slots are really the only way to do that. But here, because we don't have any restrictions besides, hey, out of these 9 fancy cakes, can you put 5 on display? Right? That's going to be the same as 9p5, which is still 15,120. Okay. So if you wanted to say it like that, that's totally fine. Right? Okay. 21. In how many ways can 5 keys be put on a key ring? Now, the thing about key rings is that they're circular. Right? And so we had that we can use the slots as long as you remember to put the circle and remember the trick that you have to just kind of pick a placeholder for your first one, right? Or it's just n minus 1 factorial, right? And so, but that's not on your formula sheet, so I want to show you how you can use the slots, right? 1, 2, 3, 4, 5 in a circle here. Maybe I can do this. All right. So we're going to move around this way. All right. I guess I could go all the way around. Why not? To create this circle. And the trick is to force this to be just pick one. Okay. So there's one choice, one placeholder, and then we can start to pick up. Because what happens, right? If I am turning these configurations, that's not a change to the order, right? And so that's what we're forcing here. And so I have 5 keys, which means that I've used 1 as my starting point, which means I have 4, and then 3, and then 2, and then 1. All right? And so I have 1 times 4 times 3 times 2 times 1, which is 24 factorial. Oops, not 24 factorial, just 24. Sorry. Or remember that you could use n minus 1 factorial for a circular permutation, right? And so if I have 5 keys, I want 5 minus 1 factorial, which is 4 factorial, which is, let's see here, using my factorial button just in case, 24, right? Which is the same. So you've got 2 options. Okay. Question 22. Find the number of different permutations of the letters of the word Massachusetts. Uh-oh. Okay. Whenever we have repeating repeating elements, okay, then this first A and the second A, in terms of a word, they're no different from each other, right? And so we need to kind of eliminate those duplicates. Okay? And so how we do that is we first need to figure out how many letters in total. Okay? So I have total letters, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay? Now I have one M. I have two A's. Oh, I'm gonna give myself some more room here. Oops. How many S's do I have? 1, 2, 3, 4. Wow. Massachusetts. C, I have one. H, I have one. Oops, one. U, I have one. And S, I've already done. E, I have one. T, I have two. When you're done, you want to make sure that all these individual numbers of letters add up to 13, right? And so just make sure that you caught them all. 1 plus 2 plus 4 plus 1 plus 1 plus 1 plus 1 plus 2 is 13. And so that's good. So what we want to do is we want to divide out any duplicates. Okay? And so what we're going to have is we're going to have 13 factorial. Okay? That's just all the letters in Massachusetts in 13 letter permutations. Okay? But then what you want to do is you want to divide out all the duplicates. Now, technically, you would be dividing out by 1 factorial for the M's, then 2 factorial for the A's. Now, because 1 factorial is just 1, we tend to not write it. Okay? Technically, it's there, but I'm not going to write it because, or maybe I will. Okay, fine. For completeness, I will. 1 factorial times 2 factorial times 4 factorial times 1 factorial, 1 factorial, 1 factorial, 1 factorial, 2 factorial, which is the same as 13 factorial. And I'll do this in light blue, which remember is the color of the optional work. So if you wanted to, I guess this would be optional too. If you wanted to skip this part, you could, as long as you show me this. 2 factorial, 4 factorial, 2 factorial. Where are all the non-ones? 1 factorial is just 1, so it's not doing anything. Okay. 13 factorial is going to be very large. Right? 13 times 12 times 11, blah, 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 blah. I use the factorial button on my calculator. 622702080. I guess this is technically optional. 2 times 4 factorial times 2 divided by 96. I'll do it in the optional color again. Because as long as you get 13 factorial divided by that, that is good. 6486480. Nice. So a lot. Use the question 23. Use the factorial formula to compute 7C4. So 7 choose 4. Okay. Our formula sheet is way up here. Wow. Here. But it is on your formula sheet, so I'm just making sure that you know how to solve these. So we have 7 choose 4. And let's do it properly. I want to see the, oops, getting tired here. 7 choose 4. No. NCR is n factorial divided by n minus r factorial times r factorial. That's the empty formula. And let's see here. So 7 choose 4 specifically is 7 factorial divided by 7 minus 4 factorial times 4 factorial. Now 7 minus 4 is 3 factorial, and so what I'm going to do, the trick, right, is to write out 7 factorial until you hit 4 factorial, and then they'll cancel. So we get 7 times 6 times 5 times 4 factorial divided by 3 factorial, 4 factorial. Show me that you know that trick. 4 factorial will cancel. And now you have 7 times 6 times 5 divided by 3 times 2 times 1. 7 times 6 times 5 divided by 6 is 35. Now you can check your work with your calculator, right? 7 choose 4 on your calculator is 35. But for marks, you have to use the factorial formula. So you have to use this. Otherwise, I can't give you marks. Okay. I think this is our last question. Nice. Question 24. How many 5-card hands can be chosen from a deck of 52 cards? Now, 5-card hands, it doesn't say anything about, okay, your first card has to be a king and then you have to draw a queen or something like that. We just want to have a 5-card hand. Okay? Which means that from the deck of 52, the order doesn't matter. I need a 5-card hand, and there's nothing that says that a 2 kings and 3 aces is different from a king, an ace, a king, an ace, and an ace, right? Same situation. And so order doesn't matter. Huh? And so here I'll specify, so 5-card hands, order doesn't matter. And that's how we know that it has to be combinations, right? And so what I want to find is 52, choose 5, which from your calculator, 52, choose 5 is 2598960. Or if you prefer to, all right, this is correct. This is all I'm looking for. Because you can use your calculator. It doesn't say you have to use your the factorial function, but 52 choose 5 is going to be 52 factorial divided by 52 minus 5 factorial times 5 factorial. 52 minus 5 is 47. Factorial, 5 factorial, which means I'm going to write out 52 factorial up until 47 factorial. 52 times 51 times 50 times 49 times 48 times 47 factorial. 47 factorial times 5 factorial. Now, Whole point was to cancel those. Okay. And let's see here. 5 factorial, let's start there, is 120. Keep that in my back pocket. 52 times 51 times 50 times 49 times 48 divided by 120. 120. Phew, I get the same answer. I was worried because I hit some buttons. 2598960. I'd say this one, using your calculator, is a lot quicker, but you can do it by hand if you prefer. Huh? Nice. All right. Good work. See you for the test.